Hi, my name is Evan Soltanic. Today I'm going to be presenting research on automated semantic labeling of parsers. This is joint work with my colleagues Carson Harmon and Brad Larson at Trail of Bits. A single popular file format will typically have myriad parser implementations. For complex and often ambiguously defined file formats like PDF, this can lead to so-called schizophrenia, in which different implementations will parse and interpret the same file differently. For example, one parser might crash on the file. Another might reject it as malformed. A third might accept the file as valid, and a fourth might be vulnerable to an exploit embedded in the file. Given a corpus of parser implementations, how can we automatically determine a maximal subset of the file format that is accepted by all of the parser implementations? To this end, given an unknown parser and input file, we want to be able to automatically extract the semantic purpose of the code in the parser. The ultimate goal being to automatically extract a minimal grammar specifying the files accepted by the parser. Our underlying hypothesis is that the majority of the potential for maliciousness and schizophrenia in the file format will exist in the symmetric difference of the grammars accepted by the format's various parser implementations. The approach is to first label the type composition hierarchy of the input files to use as ground truth. Next, we instrument a target parser using universal taint analysis to track all input bytes through execution. This gives us knowledge of which functions operate on which bytes, when, and how. Finally, we merge the results of the first two steps to produce a labeling of which functions operate on which types. We can also detect backtracking, error handling code, and perform differential analysis by varying input files and parser versions. The first two steps are prior work that have manifested in two open source tools, Polyfile and Polytracker, that are available today. An associative labeling will lead to improved and more accurate grammar extraction, which we will discuss later in the talk. Polyfile has polyglot-aware file identification to enumerate all possible interpretations of an input file. It then uses instrumented resilient parsers to maintain lexical information that is usually discarded during parsing. This produces a syntax tree for the input file that has been annotated with the byte offsets of where each object occurs in the input file. Polytracker automatically instruments a parser to track the input byte offsets of all bytes processed, as well as records control flow information of each parse. This is implemented as an LLVM pass, allowing source code to be instrumented, as well as black box binaries lifted to LLVM using a tool like Mixema or Remel. This produces a mapping of which functions operated on which bytes of the input file, when and how. For example, we can observe which bytes affect control flow. Combining the ground truth of Polyfile with the runtime information from Polytracker, we get a raw mapping of the complete set of types operated on by each function. However, this mapping is not entirely useful. This raw mapping will associate a utility function, like a string compare or decoding algorithm, with every single type on which it operated, even though such functions are completely generic. For example, PDF object streams are typically compressed, so every PDF object stream element in the input file will be mapped to whichever function in the parser is responsible for LZSS decompression. What we really want is a matching, not a mapping. How can we automatically determine the functions most specialized in operating on each type? This is the challenge of associative labeling and the problem that we address in our paper. Let's make some observations about the problem. First of all, the raw mapping is not necessarily injective. One parser might have a single monolithic function that is responsible for processing multiple types, whereas another parser implementing the same file format might have multiple functions that collectively only parse a single type. Therefore, a parser's functional implementation will rarely be isomorphic to the syntax tree of the input file. This means that there will rarely be a perfect bijection between the types and functions. The idea behind our approach is to use information entropy to measure function specialization. The entropy or genericism of a function is defined by the probability distribution of the types operated on by that function. A function with lower entropy indicates code that is specialized to process its associated type elements. Higher entropy, on the other hand, indicates a more common utility function, like character decoding or decompression. The less generic a function, the more specialized it is at processing its associated type elements. This allows us to discover the functions most closely associated to a given type. The first problem with our entropy-based approach is the case we described earlier, when a parser is implemented monolithically with code responsible for parsing multiple types at once. To solve this, we generate a so-called dominator tree of the input file's syntax tree. This is a transformation typically used in the context of compiler theory and control flow analysis. However, as we can see, this dominator tree, which was generated from a single input PDF file, accurately captures the dependency relationships between non-terminals in the PDF grammar. These dependencies will indicate when to remove a type matched to a function. Specifically, we remove a type matched to a function if it has an ancestor in the dominator tree that maps to the same function. In other words, we prune a production rule from the matching if it produces sentences that are a strict subset of another production rule that is also in the matching. The second problem with our entropy-based approach is the final case we described earlier when a parser is implemented too cohesively, with many tightly coupled functions collectively responsible for parsing a single type. If those functions are always called sequentially, then we ideally only want the single function that initiates the sequence. We once again calculate a dominator tree, but this time on the runtime control flow graph observed from the parser's execution. For each type, remove any functions in its matching that have an ancestor in the dominator tree that is also in the matching. Here we see three functions that are all matched to operating on PDF XREF objects. Since PDF load XREF dominates the others in the control flow graph, only it is retained in the matching. The associative labeling algorithm that merges the lexically annotated parse tree with the instrumented parser data runs in polynomial time with respect to the size of the parser, the size of the input file, and the complexity of the grammar. Our implementation of the associative labeling algorithm is included in the PolyMerge application, which is distributed with polyfile. It can be installed by running pip3 install polyfile. Now let us look at its results for a few different parsers and file formats. This is an associative labeling produced from a single parse of a single PDF run through an automatically instrumented version of the MooPDF parser that was instrumented with PolyTracker. Rounded nodes and dashed edges represent the type hierarchy automatically extracted from the file. Rectangular nodes are functions in the parser, and solid edges represent the matching produced by our associative labeling algorithm. As we can see, the matching corresponds to an intuitive association between types and functions. In this case, we compiled MooPDF from source and therefore have symbol names. Remember that our associative labeling technique does not use this information at all. It would produce the same matching on an instrumented black box binary with no symbolic information. Here's a similar graph generated from a single PDF run through the QPDF parser. As we can see, QPDF's implementation is much more cohesive than MooPDF. Despite this, the mapping produced is similarly intuitive. Note the correct identification of the PDF XREF table parsing function. Finally, here's a similar graph generated from an instrumented version of the libjpeg library run on a single JPEG image. Here we can see the correct identification of functions responsible for parsing image metadata from a JPEG segment. Neither of the leading automated grammar extraction techniques, autogram and MIMID, benefit from having the rich type information extracted using our approach. They rely on type information inferred from native types in the code. Moreover, the latest approach, MIMID, uses static control flow analysis that could be improved by our instrumentation to resolve indirect control flow that's only observable at runtime. Both approaches struggle with context-sensitive grammars, as well as grammars that have complex data dependencies. We expect that our richer type information should be able to resolve these deficiencies. The next step in our line of research is to integrate our results with these leading grammar extraction techniques. There are various avenues to further this research. We are interested in using the technique and tools for differential analysis of parsers. For example, we could use graph matching to map the functions of one parser to another based upon their associative labelings. This would allow us to detect feature differences between parsers. For example, we would expect Adobe Acrobat to have a set of functions specialized in operating on JavaScript and XFA forms that would not map to any functions in Poplar, which does not support JavaScript. Likewise, two different releases of the same parser could be compared to each other to determine what features were added or removed between the versions, and which functions were affected. Similar to applying the method across multiple parser implementations, we can also benefit from combining the output of multiple files across a single parser. Using a single file is limiting because the code coverage of the parser will be limited to the features implemented in that file. For example, a JPEG that does not include any EXIF metadata will not exercise any of the metadata parsing functions within a JPEG parser. Therefore, we plan to extend the approach from operating on single files to instead operate on a corpus of files, merging the output. In the event that there does not exist a ground truth labeling for the input file, for example, if the input file format is unknown, we will investigate treating each byte in the input file as its own unique type. We can then exploit the forest of taint unions produced by the instrumentation to learn the type composition hierarchy. This can also be augmented through introspection of how the bytes are stored in the data structures employed by the parser implementation. This paper has introduced a new technique for semantically labeling the types operated on by parsers. The technique works with a single run of a parser on a single file. The next step is to integrate the tools with grammar extraction techniques. Our implementations are open source and are available today at these GitHub URLs. Thank you. And once again, I'm Evan Soltanik, and this was joint work with Carson Harmon and Brad Larson, my colleagues at Trail of Bits. I'd also like to thank Sergey Bradis and his DARPA SafeDocs program, which funded the majority of this work, our partners at Galois Incorporated for their invaluable feedback throughout this research, and most importantly, the LangSec reviewers and community.